So what we'd like to do now is we'd like to kind of take everything that we've learned about circular motion and start to apply it into more real world context. So we're going to look at the motion of satellites and we're going to look at the motion of celestial bodies, so like planets and stuff like that. So before we get to that, just to refresh, you've probably heard these terms geocentric and heliocentric. So for the longest time, people believed in this thing called the geocentric model, where the Earth was at the center and the planets and the sun rotated around the Earth. Sometimes you may hear this referred to as the Ptolemaic model. Eventually, the Copernican model or the heliocentric model was introduced. This is the model we go by today. This is where the sun is at the center, the planets orbit around the sun. Galileo is also very well known for proposing the heliocentric model, and you probably also know Galileo ran afoul with the authorities at the time for proposing that, because it was considered heresy for basically what he said at the time. Now, one of the gentlemen that we're going to talk about is a gentleman named Johannes Kepler, and he built on the work of another gentleman named Tycho Brahe. So Tycho Brahe kept a lot of detailed notes about the orbital position of Mars, but he didn't really know how to analyze them. So Brahe had hired Kepler to do the analysis and to kind of figure out some peculiarities with Mars. Now, Brahe couldn't really do much with it, and part of it had to deal with he made two assumptions. First of all, he was a big believer in the geocentric model, and he also believed that planets traveled in circular orbits. Kepler came around and said, well, first of all, he was a believer in the heliocentric model, so he said the sun is at the center. And the big thing that Kepler recognized is that planets actually move in elliptical orbits. So when he accounted for that, all these discrepancies between the observations and the data that Brahe recorded, they were resolved. So Kepler's ingenuity allowed him to make a lot of progressions in astrophysics, hence why he has the laws named after him. So we're going to look at them. We're not going to look at them in a lot of detail, so we're going to just scratch the surface. And the first one, Keplers First Law, it basically states that the orbit of every planet is an ellipse with the sun at one of the two foci. Realistically, all we need you to know is that the planets travel in elliptical orbits. They do not travel in circles. Some of the orbits are very close to circular, but they're not quite circular. And yeah, that's pretty much all we really need to say about that. In terms of that word foci, a foci and ellipse is just kind of like, they're basically used to classify the size of the ellipse, like how big it is. So like, here's an ellipse, here's our two foci that essentially define that ellipse. What it's saying is that, yeah, the planet's going to travel in an ellipse, the sun is going to be at one of those foci. So for us, yeah, now to measure how much of an ellipse we have, we're going to use this thing called the eccentricity. So the eccentricity is a number between 0 and 1. 0 is a perfect circle, 1 is going to be a flat line. So the closer we are to 0, the more circular the orbit is. Venus has the most circular orbit. It has a very small eccentricity of 0.007. And the one that has the least perfect circle orbit is Mercury. It's got about an eccentricity of 0.205. Mercury's orbit is also peculiar in its own right, and it was used to do a lot of advancement of the theory of general relativity, but that's something that you'd have to read up on your own. That's my level of familiarity on that one is not the greatest. And then Earth, its eccentricity is about 0.017, so it's very close to being circular. This is why we could kind of get away with some of the assumptions we've made. They're not 100% accurate, but they're pretty good. So Kepler's second law, it has this nice way of saying a line joining a planet and the sun sweeps out equal areas during equal intervals of time. There's also some math attached to this one. We don't have to do the math. But you'll notice on this diagram here, we have these kind of two areas they're mentioning. So this first area is being swept out and this second area is being swept out. What Kepler's second law states is that the time it takes for this area to be swept out, so we'd call this time 1, and the time for this area to be swept out here, T2, what Kepler's second law says is those are equal. So the planet over here has to cover a smaller distance than it does over here. If these are happening in the same amount of time, what it means is at this point the planet's going faster and it's going slower here. So what we can kind of deduce from Kepler's second law, the closer a planet is to orbiting the sun or whatever it happens to be orbiting around, a star maybe, the faster it's going to go. The further away it is from that object, the slower it's going to go. And we know this is a consequence of the force due to gravity. The further away we get from an object, the smaller the force of gravity. The closer we are, the larger the force of gravity, hence the larger the acceleration, the larger the change in velocity. So that's really all Kepler's second law is telling us, is that the closer we are to, for us, I'll use Earth and the Sun for my context. What this is basically saying for the Earth orbiting around the Sun, the closer we are to the Sun, the faster we're going to go. The further away we are from the Sun, the slower we're going to go. And on this diagram, you'll kind of see the Sun, and it's the Earth closest to the Sun. It's going about 109,000 kilometers per hour, whereas we get about 106,000 kilometers per hour on the farthest point. So when we're doing our calculations for orbital speed with v equals 2 pi r over t, the radius we're using is an average. So we're not using any particular, we're using an average of this radius. Technically, we're using something called the semi-major axis. Let's not worry about that now. But that's all Kepler's law has to say. Or second law, anyways. The third law, it's the one, it also has a very wordy definition. So it talks about the square of the orbital period of a planet is directly proportional to the cube of the semi-major axis of the orbit. If you don't like the word semi-major axis, you can just say radius for our context in Physics 20. That works just as well. Alright, what's Kepler's third law actually say? Well, it says that t squared is equal to this kr cubed. So t is going to be our orbital period in seconds. R is that semi-major axis, or again, radius to make it more gentle for us in Physics 20. That will be in meters. So k is this thing we have not talked about. K is this thing called Kepler's constant. Now, Kepler's constant, it's basically a ratio of t squared to r cubed. And what's special about Kepler's constant is if you have two objects orbiting the same thing, the Kepler's constant for them will be the exact same. Example, in our solar system, all of the planets in our solar system orbiting the Sun, they will have the same Kepler's constant because they're all orbiting the same object, in this case the Sun. So what we can do for this equation here, if we rearrange that k equals t squared over r cubed, if we know k is constant for objects orbiting the same body, what that allows us to do is if we have two planets A and B orbiting the same star, same object, we could write that t squared over r cubed for one planet is equal to t squared over r cubed for another planet. Because these are both equivalent to Kepler's constant, and we know that Kepler's constant is equivalent for the objects orbiting the same thing. So let's use this in an example. So we have Galileo, he discovered the 4 moons of Jupiter. So Io, he measures to be 4.2 units from the center of Jupiter, and it has a period of 1.8 days. Galileo also measures the radius of Ganymede, and it has a radius of 10.7 units. So we want to determine the period of Ganymede's orbit. Right. Well, what we can do is we know that Kepler's constant is t squared over r cubed. Both moons, these two moons of Jupiter, Io and Ganymede, they're both orbiting Jupiter. So Io and Ganymede, they have the same k value, or the same Kepler's constant. What that means is we could say that t squared for Io over r cubed for Io, this is going to be equal t squared for Ganymede divided by r cubed for Ganymede. So we're interested in finding the period of Ganymede's orbit, so we would like to at least isolate for that t. Tg squared is going to be this rg cubed ti squared divided by ri cubed. And then of course we can just take the square root of all this, and that's going to give us the period. So the period, so we're told that the radius of Ganymede's orbit is 10.7 units, so it's not telling us specifically what the units are. It doesn't actually matter because both of these are just measured in these units, so they're going to cancel out anyways. So we have 10.7 cubed. The period of Io is 1.8 days. And then we're going to divide, and we're going to square that, and then we're going to divide that by Io's radius, which is 4.2 units cubed, and now we're going to square root all that. So I have units cubed up top, I have units cubed on the bottom, so the units thing is going to cancel out, and then I have days squared underneath here, but then days squared, all square root is going to give us days back. So our final answer is going to be in days, which is what we would like. So be really careful. Don't forget your cubes and squares in here, and then don't forget to square root the whole thing. So there's a lot of operations you have to deal with in here. Alright, so if we do that, we're going to get about 7.3 days. So Ganymede's period, it's going to be about 7.3 days. And that's pretty much the only real mathematical application of Kepler's third law that we would use in Physics 20. So those are Kepler's three laws. The first law, planets travel in elliptical orbits. The second law, the closer you are, the closer an orbiting object is to the object it's orbiting, the faster it's going to travel, and the farther away it is, the slower it's going to travel. And Kepler's third law, k equals t squared over r cubed. Objects orbiting the same thing will have the same Kepler's constant.